So we're going to be proceeding inductively, and the way we proceed inductively is we'll solve at each step relative lifting problems. We've already seen relative lifting or extension of lifting problems. So let me recall what we have here. We have y, we have x, and we have p, and then we have w is contained in, say, z. Okay, so let's just say it's closed. Okay, so we have w and it includes into z, and we have our function. Okay, let me make it a little more like a lifting problem. So I have my z, I have my function f, but I want to look for f tilde, which is a lift of this. But the situation is that I already have w, which is contained inside z, and I already have a given map here. Okay, I'm going to call it f tilde restricted to w. It's a bit of an abuse of notation because f tilde doesn't exist, or we don't know if it exists, but nevertheless it's clear, it makes the meaning clear. So what we want to do is, so problem is to find f tilde. So this problem is find f tilde, is to find f tilde or show that it exists, and if so, show uniqueness as well. Okay, so now there's the trivial case. So the trivial case is, of course, is if p is identity. So that would mean y equals x. Okay, here, but it is still worth doing it, because here what happens is f tilde is p inverse of composed with f. Okay, the reason I bother to look at this trivial case is because we are going to invert locally later. And here's what I will call the local lifting lemma. This is my ad hoc name. I like the alliteration. And I've formulated it in this particular way. I mean, this is standard methods, but the formulation is aimed at two things. One is to be able to treat path lifting and homotopy lifting more or less in the same way, and the second is to bring out the hypothesis. Okay, so now let me assume here, even though for the relative lifting problem it's not in general true, P is a covering map. Okay, so now, so suppose we have U contained in X is evenly covered, and it is local in the sense Z is small, let's say. So we assume f of Z is contained in U. Okay, and suppose, so first of all, suppose W is connected, then this problem has a solution. Then f tilde exists, and B is that suppose W is also non-empty and Z is connected, f tilde is unique. Okay, suppose also that this is true. You have a non-empty, then this is, it exists by part A and it exists by part B. So you see, this is very minimal. All you need is the intersection with what is there previously is connected, and it's actually pretty easy. Okay, so remember, U is evenly covered, so P inverse of U is a disjoint union of neighborhoods alpha V alpha. Okay, so what do we know? As W is connected, so is its image, there exists alpha naught such that f of W, which is connected, maybe it should become clearer that this is f of W, is contained in V alpha naught. So this is contained in one of those. Okay, so as far as this is connected, it's contained in one of those. If it's not connected, then different components may be contained in different lifts, and then you will have problems. Okay, but if it is connected, you're contained in only this. This looks like a very minor assumption, but then immediately you can define f tilde as going to be just like in the trivial case, except I restrict P to V alpha naught inverse composed with where was I? Composed with, of course, the function f. Okay, so now because W is connected, there exists this such that f of W is contained in V alpha naught, and what we know is that f of z is contained in V alpha naught also. So this implies that in fact f restricted to z of is p restricted to V alpha naught inverse composed with f. So indeed this is an extension of the previous one. Okay. So and uniqueness is because as z is connected, okay, we must have f of z is contained in V alpha naught. So f tilde of z is contained in V alpha naught and w is non-empty. I'll clarify in a moment that is. So f tilde must be given by p restricted to V alpha naught inverse composed with f. So nothing very complicated going on here, and it's just meant to bring out exactly what hypothesis was used here. So briefly with a picture, we have some character like this called z, we have some part of it w which is connected, and I have a region here which I call u, and I have sitting over it, perhaps in a different color, let's make them purple regions, a lot of different disks. Okay, and the rest of the space doesn't matter because we have the map P here, because we know the image of our space is going to be contained in this guy. So this guy goes into this u here. Okay, so it's sitting something like this, and we already have a lift when restricted to this w. So that lift must be in the union of these guys. Of course, that's just because it's a lift, but it's connected, so it must be in one of them. So this guy. Okay. If it was not connected, it could have two pieces in two different ones, and this argument fails. It's better because not everything lifts, as we will prove. Something must fail, but I'm pointing out something rather elementary fails. Okay, so there we are. We have this lift here, and now we'll just choose this component. This is our favorite component, V alpha naught. And by hypothesis, of course, p restricted to V alpha naught is a homeomorphism, so I can invert it and get to these things. Okay, so coverings are ones where evenly covered, so each one of these is a homeomorphism, and so we can, as we must have seen earlier, hopefully, yeah, so we had this hypothesis that restriction to each component is a homeomorphism. So as a result, we have we can simply invert it. And the second part, as I said, is that so if z had more than one component, the other component could go anywhere not containing w, and if w was not empty, we could still choose V alpha naught by some kind of vacuous argument, but it's not determined. But since w is non-empty, its image must be in some V alpha naught and a unique one, and so z must intersect that V alpha naught, rather f tilde of z must intersect, and so must lie fully in that. So this is the simple argument which gives you what I'm calling the local lifting lemma. Okay, as you see, very little hypothesis. All it says is the main point is that it is local. The main point is we are dealing with small enough sets so that compared to what is already so that the image is going to lie inside an evenly covered neighborhood, and that is what we will ensure next to be able to prove the path lifting result. So what is this path lifting? It's the same thing that we saw earlier. We could lift paths. So more precisely, we have the following hypothesis. We have P from Y to X as a covering map. We have a path in X. Alpha maps 0, 1 to X is a path, which means just a continuous function. And I know where I started initially. Okay. So let me call that point some continuous function. So let x0, whatever it is, or be alpha of 0, and x0 tilde be a point which maps to alpha 0. So it's in P inverse of x0. Remember, that is a discrete set. Okay, that we have there. We haven't proved it's discrete, but it's an easy exercise. We'll look at generalities later of covering spaces. So we have x0 tilde belongs to P inverse of x0. Then what is the theorem tells you? There is a unique alpha tilde mapping 0, 1 to y, of course unique provided it's continuous, and it exists, it's continuous, such that we can just draw it a commutative diagram. We have y to x, and we have here, and what is the map here? This is the domain of this is 0, 1. This map is alpha. This is alpha tilde, so such that this thing commutes, and alpha tilde of 0 is x0 tilde. So you notice this is already a relative lifting problem, except that it's relative starting at only one point, but still it's relative. Okay, and this is what we have to prove. This is what takes a little bit of work. Okay, so the key idea here, a key idea, and additional to what we have seen before, is by Lebeg number theorem. Okay, which you recall will tell you that if your space is compact and you have a map, in this case it's 0, 1, and you have an open cover, okay, of this compact set, there is a Lebeg number, so anything small enough is contained in that open cover. Okay, I'll say this again once I state the consequence. By Lebeg number theorem, there exists epsilon greater than 0, such that if j is contained in 0, 1, and length of j, so length of so let me say diameter of j is less than epsilon, then alpha of j is evenly covered. Okay, there is a small argument here, so let me recall what Lebeg number theorem is. So here we have 0, 1, and here we have a topological space. Okay, this is a statement about metric spaces, but X doesn't have to be a metric space. We need our codomain, the domain, to be a metric space. We have a path alpha. Alpha may be wandering around everywhere. And this is X, we have Y here, and there's a bunch of evenly covered neighborhoods which cover X. Let's look at the inverse images of them. Okay, they might be this one and then this one, etc. So the inverse images of these will form an open cover of 0, 1. That's simply by definition, because you have an open cover, you pull back the neighborhoods, they form an open cover. Okay, now every open cover has a finite subcover, but there's a nicer result in the case when the domain is a metric space, namely you can find an epsilon, so that if I take any set of size less than epsilon, then it is covered by an open set. So that means its image is evenly covered. Okay, so hence, so pick n, let's say pick capital N, which is greater than 1 over epsilon. Okay, not 1 over 3, 1 over epsilon. Okay, and subdivide. Subdivide 0, 1 into n pieces. Here we are. Okay, and now we'll define inductively alpha tilde on 0 and k by n. Okay, using local lifting lemma. Well, I can write formulas and you can read formulas. It's easier to see it with a picture. Okay, so suppose we have defined it. Let's look at the first interval. What do we know here? The first interval is small. Okay, and the function is already defined on the purple part, which is a point. Okay, it's a single point. Single point is connected, and this whole interval maps into this whole thing, maps into an open, evenly covered neighborhood. That's what our Lebeg number theorem told us. So local lifting lemma will tell you the lift already given at this point, which was alpha tilde of 0, extends to this set. Okay, and now suppose we have defined it up to here. We want to define it on the new interval. Okay, which is here. Okay, so I'll just concentrate on the new interval, and the new interval intersected with the previous set. Okay. And when you look at the new interval intersected with the previous set, then what happens is this is connected, and we will define the map on this extending that. Okay. This extension can be exists because again of the local lifting lemma. We'll repeat this process and extend it across all of n. Yeah. So this is the quick sketch of the argument. We'll partially repeat this because homotopy lifting is very similar to this in nature. So what we'll do in the next video is we'll look at the same thing. I'll write it slightly more formally, and then we'll turn to homotopies and see that basically the same thing will let you lift homotopies as well. Okay. But in between the two, we'll see what we gain from path lifting and why we want to lift homotopies as well. So that would be what happens next.